Alright, in this video, I wanted to talk about a couple concepts that we use to think about the forces of evolutionary change. So, what are the things that are going on that cause evolutionary changes in populations? We've considered a couple of these already, but I want to add a few more forces that lead to evolutionary change to our list in this video. So, let's remind ourselves that allele frequencies determine if evolution has occurred or not. So here I've got two populations. I've got a starting population here with all these different colored spheres. And then I've got a population, it's smaller later on, 5 generations later, that is composed of these spheres in the second circle. And remember that we apply this definition, that if evolution has occurred, the allele frequencies in a population are different than they were earlier in the history of that population. So if we look at the allele frequencies for this starting population, they're listed right here. We say that the 5 alleles for this trait are equally distributed. Each one of them occurs 20% of the time, or 0.2. But then 5 generations later, in the same population, so we're looking at the great-great-great-great-grandkids of this population, the allele frequency is now different. One of the alleles has increased up to 40%. Another allele has decreased down to just 6% of the time. So the allele frequency has changed, evolution has occurred. So remember, when the allele frequency changes, that's evidence that evolution has occurred. And today we want to discuss the many things that can cause these allele frequencies to change. So we've discussed some of these previously. We're going to lump these all together into things that are forces of evolutionary change. Again, we've discussed a couple of them previously. The two we've specifically discussed before are natural selection and sexual selection. So remember, in either of these cases, a certain allele is beneficial in that it allows the organism to survive better in its environment, thus having more offspring and making that allele more common. Or in sexual selection, it allows the organism to reproduce more successfully and more often, having more offspring and making that allele more common in the population. So we've talked about those in other videos, but today we want to think about some different forces of evolutionary change that aren't quite as obvious. So we're going to talk about 3 of them. We're going to add mutation to this list. We'll also think about migration, how that can affect allele frequencies. And finally, we'll think about a concept called genetic drift. So let's address each of these one at a time and just apply a little bit of a definition. So we'll start with mutation. Mutations can create new alleles in a population. So if an individual receives a new mutation, we might create a new allele of a gene. If we add an allele to the population, we by definition have changed the frequency of the alleles. So let's look at this in a little bit of a graphical way. So if we think about the allele frequency for a gene in a population, and let's say this gene has 3 alleles, and they're distributed in this way, so that one is the most common, and the other 2 make up almost a quarter each, about. And then in this population, a mutation occurs. So if we get a mutation event, and that specific mutation by random makes a new allele in this gene that we're considering, we're going to add a 4th allele to our list. We'll put a wedge in for that, and we have changed the allele frequency. The population is now different. So we would say evolution has occurred. So that's how mutations can lead to evolutionary change. Mutations add new alleles, which changes the allele frequency. So mutation's pretty straightforward. What about migration? So migration is when organisms move between populations. And when an organism moves between the populations, they bring their alleles with them. And bringing those alleles can change the frequency of the allele distribution in the population they move to, and potentially in the population they moved from. So let's think about this simple example where we've got 2 bird populations separated by a mountain range. And something about the bird population on the left side of the mountain range has selected for birds with a certain pigmentation and the dominant allele. So population A has a allele frequency of the dominant allele that's 100%. Whereas on the other side of the mountains over here, some other force in the environment has led to selection for the recessive allele. So in this population, they have an allele frequency that's 100% for the recessive allele. If one of these birds from either populations was able to cross the mountain range and then intermingle with the other population, and then they mated, we would introduce the alleles from this bird into the other population. This bird would bring along its recessive alleles into the population on the left. We would add recessive alleles to the population. We would have changed the allele frequency, and evolution, microevolution, would have occurred. So migration, moving alleles because individuals move, is a force of evolutionary change. All right, so the final one we want to think about is genetic drift. Genetic drift describes sort of a random sampling event that occurs in a population, where some event or some consequence of the environment causes a subset of the individuals in a population to survive. And then the allele frequency in that subset of the population might be different than the original population. So this image is showing us an animation of 5 successive random sampling events. And we're going from a population that's 50-50 for these two alleles. And just through successive random sampling events, we're actually going to end up with a population that has a 100% frequency of the blue allele. Okay, so random sampling, just grabbing a group of individuals from the population, can result in a new, different allele frequency. So we're going to actually think about a couple specific examples of genetic drift. So let's think about one of those. One specific example of genetic drift is something we call the founder effect. The founder effect occurs when a group of individuals leave one population, move somewhere else, and those individuals start the new population. So they're the founders of a new population. Some famous examples of this were when certain religious communities, certain people from religious communities in Europe in the 1700s decided that they would move to the Americas and start a new population here. So religions like the Mennonites, they were in a larger population in Europe. Some of them decided they would get on a boat and move to the Americas, and they started a new town and a new population here. So in the founder effect, some individuals leave an original population and start a new population. So I think this animation will start over in just a second. So here, this small group of individuals leave this larger population. By chance, they have a different allele distribution than the original population. And then the new population works from that new allele frequency or allele distribution. And we can see that the old population and the new population will differ in their allele frequencies. And this was because of the random nature of the alleles that came with that founding population. So that's the founder effect. When a group of people leave a population, the random choice of which group leaves results in a new allele distribution. If we compare the two populations, the new population has a new allele frequency. That's microevolution that has occurred. All right, let's think about one last example of genetic drift. So another example of genetic drift, random sampling that results in new allele frequencies, is what we call a bottleneck event. A bottleneck event is when we have a large, more diverse population, and then only a few individuals from that population survive. And the alleles that they carry are now the only alleles present in the population. So here's an image that demonstrates a bottlenecking event. It's actually using a bottle to make it a little easier. So we've got this large original population inside the bottle, and we've got a diverse group of alleles here. But again, the event only allows a few individuals to survive, the ones in the glass. And they have a different allele distribution than the original population. Again, if we change the allele frequency in the population over time because of this bottlenecking event, we say that evolution has occurred. So let's think of a couple real-world examples of bottleneck events. One of them might be a natural disaster, where a natural disaster maybe leads to the death of a large portion of the population. So wild animals here. Let's say a hurricane blows through and the habitat for a bunch of animals gets destroyed, some of the animals die, and only a few survive. If those few animals that survive have a different allele distribution than the original population, then we've experienced this genetic drift leading to this evolutionary change. Another real-world example of how this works is poaching. So humans hunt certain animals, and the animals started with a large population, and then if humans overhunt them, we have a much smaller population left. And that smaller population might have a different allele distribution than the original starting population. And that act of humans overhunting an animal population could lead to genetic drift and evolution. So that's where we'll stop. We've added these 3 additional forces of evolutionary change: mutation, migration, and genetic drift. And again, we should be considering those along with natural selection and sexual selection. So I'll talk to you again soon. As always, let me know if you have questions on the discussion board, and we'll talk later.